Okay, hi and welcome to Notes 8.8, which we're going to talk a little bit more specifically about exponential growth. We already know a little bit about exponential growth, so it's not entirely new to us. However, we need to look at it a little bit different because we might not see it as simple as we've seen before. So this would be an example of an exponential function, and we'd realize that that's our initial amount there, also known as our y-intercept. This then would be your growth factor, right? So that's our B. And that would represent something tripling or growing by 300%. And those are nice and easy, and we can kind of plug them in and see them that way. However, in doing that, sometimes these growths are considered as a rate or a percent. You may be only growing by a portion of a time. So we have to look at the growth a little bit different. Let's just recall before we go any further that growth means in visual shape, right? That we're going to be somewhere near our asymptote, and then that's going to increase, and somehow, or not somehow, but increase further and further away from our asymptote here, okay? Meaning that we're getting farther from it, and that would be a positive growth. And there's also the opportunity for a negative growth, meaning that it gets farther from the asymptote, but in the negative direction. So again, we're going to explore when this B, this growth factor, is as a rate. So what does that look like? Well, let's take a peek. Here's our A value. We're comfortable with that. That's our initial amount. But instead of having just a B, we now have this in 1 plus R inside of our parentheses. And that may look a little bit odd, but let's talk about it in some terms that maybe you're familiar with. So let's scoot over here. So considering growth, is this B value as 1 plus some percent. Again, just referencing R, I used a percent sign there. What does that mean? Well, let's examine this question here that I've written out for us. Is what's the tax on $1? At least in the state of Michigan, that is, right? Sales tax in Michigan is 6%. So what is the tax? What would you pay on an item that's $1? So that would be looking at the next example here. It says, how much do you pay for a candy bar? Well, how do you find out how much tax is on a dollar, right? You multiply the dollar by the tax. So what would we multiply by? We would take 1 times 0.06, because that would be in the decimal form. And you'd find out what? That it would be 6 cents, right? So you find out that 6 cents is how much they're going to charge you. But how much do you pay for the candy bar? Well, the candy bar is originally $1. But now you're adding in the rate that they charged you, or the rate of growth. So they're charging you a percent, an exponential percent, right? They're charging you 6%. So you'd take that percent that would calculate out whatever that percent of growth happens to be, and you'd add it to the dollar, meaning that you'd pay $1.06 for your candy bar. What happens if we had a candy bar that was $2? Well, we'd be multiplying by not 6%, we'd be 6% twice, or essentially 12%, or 12 cents. And so you can see that there's a, oops, that should be a 2 because it's $2, right? $2.12 is what we pay. What you're doing here is essentially what we're going to do with our B value. We're going to take 100% of the original, right? So this represents 100% of the original item, whatever its initial cost is. And then we're going to add to, just like we added the tax, we're going to add on whatever that percent increase happens to be, or percent growth. And so when we look back over here, what we're seeing then is that we're going to calculate our B value, right, by looking at or taking our 100% of the original, adding the increase that comes from whatever rate they give us, and that becomes your B value. So instead of writing just B, we look at it a little bit different as 1 plus R so that we can be a little bit more specific with it if we're given rate. Okay, Mr. Hallam, what does that look like? Well, let's do a quick, not very exciting example, but a kind of a neat one. All right, so we've got an example here about some hospitals. It says, since 1985, the daily cost of patient care in community hospitals in the United States has increased. There's it is telling you that it's most likely a growth, right? About 8.1% per year. As soon as you see an increase and it's not some kind of constant rate of change, you know that you're dealing with an exponential function, okay? And that's what we're getting from that. So it goes on to say, and that's our rate increase. So if we look back, finding our information, hold on one sec, we got a little stuck. Get back unstuck here. So you can see there's our R, that's our percent of increase, right? We're going to add that to 1 to be able to find out how much our B value is actually going to be. All right, let's keep reading. In 1985, such hospitals costs were an average of 460 per day. So in 1985, we're starting with a per day cost, which is our initial amount, because that per day cost is increasing. So that's your initial amount, your A. It says write a model for the cost of this hospital care. So we're just going to write the function at first, and part B will actually evaluate it. So what I want you to do for each and all of your homework is make sure that you write down this new rate version of our exponential function. Does it always apply? No. If they give us something like tripling or doubling or some b value right off the get-go, we just use that. But if they say anything about a rate, I want you to write this down. And really for your homework, I want you to practice. So you're going to memorize this because I'm not going to give it to you. You're going to write that down on the top of each of your homeworks. All right, so now that we have that, we already identified our rate. So we wrote R, and as a rate, we've turned it into a decimal. A percent rate, right? So it's 8.1%, but that changes to 0.08 as a calculation, right, as a decimal. And we know that our per day cost or our initial amount is $460. So really all we're left to do is kind of plug those in and then kind of clean up the formula. So let's start off by saying that y equals 460. That's our initial amount. That's where A would be located, right? And then in the parentheses, I'm going to write this out. Eventually, you won't write this part. You'll just kind of calculate it together. But let's write it out just so we can see it. We got 1, which represents $460, the original amount, plus that increase per year, right? Because it's increasing per year. And the increase per year is 0.81. And that's raised to the t. Again, we're just writing a model. We're not evaluating, not plugging anything in for t, because that's our input, right? And that's our output. T's our input, y's our output. So there's a nice model for it. Let's clean it up and make it look like it should. Okay, so we get 460 times 1.081. That's your growth factor. So this is 1 plus the rate, which turns into, by adding them together, into your growth factor. And that's kind of what I want you to see for these rate problems in exponential form. All right, so part 2 then says use your equation to approximate the cost per day in the year 2000. So really then we need to figure out how many times or how many things have occurred since 1985. So we're going to take 1985 and 2000 and find the difference of them, which in this case we're going to find that it's 15, which means that we're going to evaluate this function at 15. Let's go ahead and use function notation. So we're going to say the function in terms of t in this case, well, let's write it out. We'll say the function's in terms of t for $460 per day initial with a rate increase of 0.81 t. Okay, now we'll go ahead and evaluate the function at 15. So this is us plugging in that x coordinate, the t coordinate in this case, is going to be 460 times 1.081 and then 15 up here. Now, if you're calculating this, I'm going to recommend that you do it in chunks since you don't type it all in. Why? Because there's more likely of a chance for you to make a mistake. So especially if you don't use the parentheses correct. I would put this in first, I would calculate that, and then I would come back and multiply my initial amount. That's how I would put it in my calculator because that leads to less mistakes for me. Right? Your calculator's super smart, but you have to know how to direct it. So once we did that, if we put that in our calculator, we're going to go ahead and calculate it out. We're going to find out that it's going to be $1,479.60 per day in the year 2000. And if we wanted to, we could change that to 2017, our new year coming, and we could calculate how much it is per that. Is it exact? Does it stay on that model? I don't know. Don't forget, this is an increase. So we're going to see some really slow increase like this, right? Because it's 1.018. It's barely bigger than 1%. So it's going to be a real gradual curve. Is that accurate? Could totally be. But for this model, what they asked for, this would be an accurate representation. All right, so that's exponential growth. Just to kind of review so that you're clear on it, that the B now is a form of 1, which represents 100% of the original amount, that initial amount, plus whatever that rate of increase happens to be. Okay, so if they say anything about a rate, you're going to calculate B this way. And that's really the only thing different with this form of it. All right, thanks for watching, and we'll see you in class.